Hi everyone, this is Andrea and you're watching my presentation for the 2026 SFP conference on performance-based design. I will talk about how to make optimal use of fair tests for performance-based design, and I advocate the need for optimized testing protocols. Before we start, briefly about myself. I'm a postdoctoral researcher at Ghent University and I do research on probabilistic methods in structural engineering. I want to start this presentation from the main reason why so many people gathered here in Singapore, and that is performance based design. Or, in different words, we are here because we recognize that countries around the world are undergoing a transition from prescriptive design to performance based design, where we enable any design solution as long as we can demonstrate it's safe enough. Prescriptive design is based on classification systems that are derived from standard testing, which raises the question of which tests do we actually need for performance-based design? Can we use standard testing, for instance, a furnace test? Or do we need application-specific tests? For instance, here in the background, you see the radiant panel that we have at UGent, which can be used to simulate localized fire exposures. Clearly, we cannot make a new test every time we need to do an assessment. And that's because tests are costly and time consuming, our resources are limited, and we want to be mindful about the environmental impact of our experimental campaigns. What we do want instead is that those times we actually test, we do that in an optimal way. And that means using optimized testing protocols. So, what is an optimal testing protocol? The answer to this is actually pretty simple. That is a protocol which provides the highest expected utility for the assessment it supports. Or, put in a different way, if we were able to quantify the expected utility of a test before its actual execution, we could iterate over this quantification until the protocol is optimized. And at UGent, we develop a methodology that does exactly that. The methodology looks like this. We start by setting the goals of our experiment and we select target parameters, which are some uncertain parameters on which we want to gather information using our testing campaign. And then we define an experimental protocol, which consists of the combination of procedures, for example, furnace testing, concalorimeter testing, radiant panel testing, and so on, and experimental design parameters, which are all the controllable features of those procedures. For example, what is the temperature inside the furnace? What heat flux are you exposing your sample to? Where are you putting thermocouples? And so on. Second, we built two models. An experimental model that produces possible outcomes of your experiment, and a performance model, which maps the target parameters to the actual performance metric we are interested in understanding. This could be, for example, failure probability of a structure, it could be some risk metric, and so on. Then we do a pre-posterior Bayesian analysis, meaning that we use the experimental model to simulate multiple potential experimental outcomes and we update the distributions of our target parameters based on those outcomes. Finally, we define some measure of utility to understand how much the update improved our understanding of the target parameters or of our target performance metric. And finally, we take the expected value out of all the possible realizations of the experiment and we iterate until we achieve an optimal point for the expected utility. Now, this expected utility can take different forms. It can be a measure of uncertainty reduction, it can be a measure of economic value of information, or it can capture the environmental benefit of the information you gathered during the test. In the next slides, I will show you two examples of how this methodology works. We will do that first in the context of furnace testing and second in the context of concalorimeter testing. So let's start with furnace testing. We know this test has several benefits and it has been around for a long time, but it also has several limitations, such as the fact that it doesn't represent a real fire and the fact that the actual safety of a fire-rated product remain unknown. We don't know failure probability of a structural element which has a given tire resistance. So the question is, can furnace testing be useful at all for performance-based design? And if so, how should we design the testing protocol to best support performance-based design? To address this question, I will consider an example. We will take a reinforced concrete slab exposed to natural fire, and I'll assume that our target metric for the performance assessment is the failure probability, which is the probability that some measure of demand exceeds some model for capacity. The way we usually do this is by defining distributions for demand and capacity. Here, I'm assuming that the capacity is deterministic, and we take the failure probability as the area where the demand exceeds the capacity. The problem is that we also have uncertainty on the distribution parameters. And that means we will have different distributions for demand and capacity and different realizations of failure probability, which means that also the failure probability has a distribution. And the idea is that gathering new data will reduce uncertainty in the distribution of failure probability, and therefore we will be more confident in its estimation. So let's go through the methodology step by step and see how this actually happens. We start by defining target parameters. In this case, I consider 4 parameters. The first one is the specific heat quantile. That means we consider this probabilistic model for the specific heat. Here you see the specific heat against the temperature. And we assume that for a given simulation, the same realization of quantile holds at all temperatures. Then we do the same for the conductivity. Again, this is the probabilistic model of conductivity as a function of temperature. And then we have the strength of concrete and the yielding strength of steel. Next, we need to assume prior distributions for these target parameters, meaning distributions that reflect our current state of knowledge on these parameters. And here they are. We assume uniform distributions for the quantiles, which means that the quantile can take any value inside its distribution. And we have log normal distributions for both the compressive strength of concrete and the yielding strength of steel. Next, we built an experimental model that should reproduce potential outcomes of our experiment. In this case, we are dealing with furnace tests. So we start from the certain parameters, we run a heat transfer analysis where we get the temperature development inside the slab as a function of the heating exposure in the furnace, which is the ISO 834 curve. And then we use this temperature time history to calculate the time history of the capacity of our slab, which is this curve, and we compare it to the capacity, the bending capacity of our slab. When these two curves intersect, we identify the failure time, which will eventually determine our fire resistance, which is the parameter that we get out of the furnace test. Second, we build a performance model that in this case should take the uncertain parameters and map them to failure probability in the natural fire. So we start from the uncertain parameters. Again, we run a heat transfer analysis where in this case we expose the slab to a compartment fire. In this case, we consider a single one, but that can be done also in a probabilistic manner, meaning considering different temperature curves for the compartment. Then again, we map this time history of temperature to a time history of moment capacity for the slab. We take its minimum value and we compare it to the cumulative distribution of the loads. So this graph shows on the vertical axis the probability of exceeding the values that you see on the horizontal axis. And if you put the minimum value we get from the capacity, you compare it with this curve, you will get, by definition, the failure probability. The failure probability generally spans several order of magnitudes and assume very small values. So to ease the manipulation and treatment of failure probability, we just map it to reliability index, which can be done through this equation. And the idea is that a higher reliability index indicates a lower probability of failure, meaning a safer structure. Next, we do a pre-posterior Bayesian analysis. So let me start from explaining what is a posterior Bayesian analysis. This is a statistical procedure where the prior distribution of some uncertain parameters is updated based on experimental evidence. And this is generally done using Bayes' theorem. Bayes' theorem can be formulated as follows. It tells us that the posterior distribution of our uncertain parameters conditioned on the data we observe, so this is just a posterior distribution of our parameters, is proportional to the product between the prior distribution, meaning our prior knowledge on these parameters, and this is represented by the distributions that we defined in the beginning, multiplied by the likelihood, which is the probability of observing the data conditioned on the uncertain parameters. And in this case, we will assume that this is a normal distribution centered around the prediction of our experimental model and with a standard deviation of 2 minutes. So all this works if we have the data. But as I mentioned in the beginning, we want to do this analysis before we run the experiment, meaning that the data are actually not available. And in this case, we will perform a pre-posterior analysis, meaning that we generate multiple potential experimental outcomes using our experimental model and then iterate over the posterior analysis multiple times for each realization of our potential data. And this is what I'm doing here. Here I generated 100 realizations of potential experimental outcomes from our furnace testing. And then for each of these realizations, I'm doing a posterior analysis. So I'm updating the prior distributions based on the observed data, which is the failure time. So for example, for the first realization, which is this one, I'm taking the prior distributions and I'm updating them using some numerical solution of Bayes' theorem. And you see, this is the blue ones are the posterior distributions of our uncertain parameters if that result was observed during the test. And as you may expect, if you do that for a different realization, now I'm doing for realization number 80, you will get a different posterior distribution. And then we take our performance model and we map these distributions to distributions of our reliability index. Here you see in the background, in black, the prior distribution, and then all these are posterior distributions for different realizations of the furnace test outcomes. And here you observe two things. The first one is that the reliability index may shift rightwards or leftwards based on the data we observe. So if you observe a larger fire resistance, you expect a larger reliability, meaning a safer structure, and vice versa. If you observe a lower failure time in the furnace, you may expect a lower reliability index to materialize. Second observation, you see that all this realization, for all this realization, the distribution has shrunk, meaning that those outcomes reduce uncertainty in predicting the reliability index. So now we want some measure to understand how much this uncertainty reduced. And that's what we need to define expected utility. So again, this utility should be a measure of uncertainty reduction, and that can be achieved through a metric called information gain. Information gain is defined as per this equation, which has a very simple interpretation. That's simply the difference between the amount of uncertainty we have in the prior and the amount of uncertainty we have in the posterior. And the result is taken across all the possible realizations of our experiment that we have simulated before. And then we take the expected value, which provides us what we call expected information gain. This is a graph showing the results of my analysis. Here you have the expected information gain on the vertical axis and the number of hypothetical tests on the horizontal axis. And this is the trend of the expected information gain. From this, we can draw two main observations. The first one is that the expected information gain is always positive, meaning that in expectation, running any number of tests will reduce uncertainty in predicting the failure probability of the slab exposed to a natural fire. Second observation is that the expected information gain first increases and then tends to plateau, meaning that early experiments are more informative than later experiments, and that from an information theoretic perspective, it doesn't make much sense to go beyond the point where the expected information gain actually plateaus. And that means we can use this analysis to identify an optimal number of tests that in expectation will reduce our uncertainty, and going beyond them will not provide any benefit. So in this case, we may want to run between 3 and 5 furnace tests. So this is the final result of our analysis, and it tells us that an optimal experimental protocol will be defined by this number of tests. Now I want to give you another example in the context of concalorimeter testing. We consider a PMMA sample exposed to a heat flux of 20 kilowatt meter square, and we assume that the target metric we want to assess is the ignition time of this sample. We will also assume that the ignition time is normally distributed, and for this example, this normal distribution will be both our experimental model, meaning the model we will use to simulate potential experimental outcomes, but it will also be our performance model, because again, now the scope is reducing uncertainty in predicting the ignition time. The uncertain parameters of interest are the mean and the standard deviation of the ignition time distribution. And again, as before, we assume some prior distribution for them. In this case, I took two uniform distributions and I calibrated those values based on literature values for the ignition time. And then, if you take these distributions and you input them in our normal model, we will get our prior distribution of ignition time. And this is what we want to reduce uncertainty about. Again, as in the previous example, the only design variable we will consider is the number of trials. So the question is, how many trials do we need for concalorimeter testing to reduce uncertainty in this distribution? Again, we follow the same methodology I showed you before, I will skip the first two steps, which we already discussed, and go into the pre-posterior Bayesian analysis. So again, we start from the prior distribution of our uncertain parameters, and we use the model to simulate multiple potential outcomes of our experiment. And these are the results. So we have on the vertical axis 500 realizations of ignition time, and this will be done for different number of trials. This graph is for 3 trials, and we will all the way up to 30 trials. So this is one realization of 3 potential outcomes of our experiment, and these are 30 realizations of potential concalorimeter measurements if the selected number of trials was 30. And then, again, for each of these realizations, we do a posterior analysis where we update the prior distributions. So here you see a comparison between the prior and the posterior for the mean and from the standard deviation. And then we can map this to a posterior distribution of our ignition time. You see that in this case, for 3 trials, the distribution didn't update much. But for this other example, this is realization 1 for 30 trials, you see that the update is much more significant for both the mean and the standard deviation, and that will result in a more significant update of the ignition time. So now again, we want to quantify the utility of these updates. And again, we will do that in terms of uncertainty reduction, which again is given by the information gain metric. And the graph looks like this. Now, again, we have the information gain, the expected information gain on the vertical axis, and the number of trials on the horizontal axis. And I repeated the simulation 2 times to check the robustness of my code to randomness. And you see that, as before, the expected information gain first increases and then plateaus. So the trend is similar to before, indicating that first, any number of tests has a positive expected information gain, meaning is expected to reduce uncertainty in the ignition time. And then, again, the trend plateaus, meaning that from an information theoretic perspective, it doesn't make much sense to go beyond the point where our curve starts to plateau. So again, this would identify an optimal number of tests for our testing campaign. Up to now, we remained in the domain of pre-posterior analysis, meaning we have done all this in the assumption of being before doing the test. So the question may arise of how does this compare to what we obtain if we actually test? And to check that, we took some data from the literature. Here you see 100 realizations of measured ignition time in an experimental campaign. I divided them in 3 datasets of 30 trials each, and I checked the actual information gain these tests give us and compare it to the expected information gain we get from the pre-posterior analysis. And this is the result. Here you have the marginal information gain on the vertical axis, meaning how much the information gain will increase as the number of trials increases. And then I'm comparing the curves for pre-posterior analysis and for the posterior analysis. And you see that the trend matches very well and confirms that beyond 15 to 18 trials, we do not have any significant marginal information gain, confirming that our predicted optimal number of tests is within this range. Up to now, I show you how to optimize the number of tests, but that's not the only thing we can do. We can optimize any experimental design parameter. For example, we can optimize testing temperatures. Here you see an example of a work we're doing at UGent, where we are building a model for the temperature-dependent strength of glazing. And we use the methodology I've just discussed to understand at which temperatures we should perform our tests. For example, you see that the analysis shows that the expected information gain is maximum is if the temperatures we chose are 225 degrees and 275 degrees. We can also optimize sensor placement. For example, where do you place your thermocouples to reduce uncertainty in the temperature profile prediction? And so on. You can choose any experimental design parameter that you want, as long as you have a model that can capture its effects on the experimental outcomes. Finally, we can follow two different strategies for this. What we've been doing up to now is called batch design, meaning that we optimize the experimental protocol and then we run the experiment. But we can do another thing, which is sequential design, meaning that we optimize a first batch of experiments, we run them, and then we use the results to update our prior distributions and run the optimization again to understand, based on those previous experimental data, what will be the optimal experimental protocol that will maximize utility for the next batch of tests. And then we run the batch again, and we can repeat this multiple times based on constraints we have in both in terms of time of running your test and in terms of calculation time for running the optimization. So this leads me to the conclusions of my presentation. We saw that performance-based design require optimized testing protocols, which can be obtained by quantifying and maximizing the expected utility before execution. And I show you a methodology that you can use to perform this analysis. And finally, we can optimize any experimental design parameter we want as long as we have a model which is able to take into account the effect of that design parameter on the potential outcome of your experiment. And that's it for me. Thanks a lot for your attention. Thanks a lot for watching. Please, if you have any comment or questions, send them over to me. Thanks a lot.